So the next speaker is Savary from Inria, and for ahead of time generation of GPSA projection in RISC-V embedded cores.
Thank you. Hello everyone. I'll present you my ahead of time generation for GPSA protection in RISC-V embedded cores, no more HPC. It's time for embedded systems. So, embedded systems, as they are remote, they are vulnerable to more invasive attacks than cyber ones, such like fault injection attacks, where the goal is to change the internal state of the processor to induce errors in the executed program. Multiple means can be used, like a laser, clock or power glitch, and electromagnetic pulse. And these faults can corrupt data, so it's not covered here. Here we want to ensure the control flow integrity. So ensure that all the instructions are executed and in the right order and the right instructions. Existing solution to ensure control flow integrity relies on redundancy and authentication and can be implemented both in hardware or software. An existing solution is GPSA and CSM for global path signature analysis and continuous signature monitoring, where the idea is to give each instruction a signature depending on the previous instructions, and such that it follows the execution order. And we also want to protect normal control flow changes, so we have to protect the control flow instructions with patches to correct their signature to the destination signature. And during the execution, a dynamic signature encodes each executed instructions and can be compared to a reference computed ahead of time with and modified with patches when executing control flow instructions. This technique is implemented both in hardware and software. Hardware to manage the dynamic signature and encode every executed instruction, and in software to generate all the references and patches needed to verify the control flow. An implementation of GPSA and CSM is SciFi on a pipeline. All the control signals leaving the decode stage are encoded into a dynamic signature and are duplicated to detect faults into the later stages of the pipeline. They also need a compiler to generate the signatures and add some instructions to access the signature, the references and patches into the memory of the program. This solution, this solution ensures control flow integrity, code, and control signal integrities, but as the GPSA values are generated by a compiler, you have to have access to program sources, and you cannot handle dynamic behaviors like indirect jumps cannot be protected by this technique. But we want to protect any program without having to recompile it. So another solution rely on an interrupt to generate the signature and patches during the execution of the program under the level of the system. And so when during the execution of the program, when a control flow instruction is executed, if a dedicated memory added to the core is queried for the GPSA values of this instruction, if they are missing, an interrupt is raised, and GPSA routine, software routine, generates the missing values. Then the execution resumes with the needed values. This solution also requires a dedicated memory to store and manage the values generated by the routine, and some operators to accelerate the execution of the routine. So this solution allowed dynamic behaviors to be handled by a GPSA protection, but it has big overheads, heavy overheads, both in performances and in area, and does not take advantage of previous execution. It's always start from zero in the control flow graph. So that's why we propose to compute most of the GPSA values ahead of time upon installation of the program, and rely on interrupt to fill the gap for dynamic behaviors, indirect jumps especially. So from the binary file, we build a control flow graph and compute each signatures and patches. Then they are stored in a structure ordered by pieces of the control flow instructions, where there are also offsets that are stored to link the different lines with them, within the structure to follow the control flow graph of the program we want to protect. So during the execution, every executed instruction is encoded into the dynamic signature, and a line pointer points to the line corresponding to the next control flow instructions that will be executed. When we execute this instruction, the values in the memory are used to verify the control flow and correct the signature to the destination. If the branch is not taken, the pointer goes to the next line. If the branch is taken, the offset is used to modify the pointer to point to the next line that will be encountered. And when we execute an indirect jump and return instruction here, we do not have offset or patches yet, so we go into an interrupt and execute the software routine to compute a patch and an offset from the known values at this point of the return instruction and its target. And now we have the values available. The execution of the program can resume. So we implemented this solution on the COMET RISC-V processor and evaluated it with the mbench-IoT benchmark. We achieved, so the graph represents the slowdown factor compared to the baseline processor, so unprotected processor. In red, it's the previous solution, so with the patch and signature memory, only relying on the routine to generate all the GPSA values. And in blue and green, it's the Rohou approach. In blue, just with the routine, and in green, with some additional registers to store and take advantage of temporal locality of return instructions. So we achieve a slowdown factor of 1.82 compared to the previous 3.3. It's much better. And area overhead of 30% compared to the previous doubling the size of the core. It's also much better. And we handle dynamic behaviors. So we have a more general case compared to sci-fi, for example. So I present you a GPSA solution for commercial off-the-shelf binaries with reduced overheads compared to previous approach. And we still have to reduce the routine overheads. That's the only overhead left in the performances, and also tackling the CRC lenses to reduce the memory needed for the solution. Thank you.
Thank you. I think we've got time for one or two questions. Yes, upstairs, at least, or here also.
Hi there, thanks for the talk. I may have missed this, but I don't think you said anything about what the qualities or attributes of that chaining function that you use for the signature, that chains the signature from one instruction to the next. So I'm wondering what the characteristics of that function are, and which of those characteristics does the security of your solution depend on?
So the function used to encode the signatures and the instructions is actually CRC32, because the order of the encoded instructions matter in this function, and it's easy to invert, to retrieve and roll back basic blocks for the routine to generate signature or retrieve signatures and patches. Yes.
Hello. So there is a CFI spec on RISC-V, and I was wondering how it compares to your work.
I'm sorry, I don't know. I never looked at this solution. But it would be interesting to compare to an existing approach. I'm sure.
Okay. So thank you, Louis. I guess